of the hour, and we'll go ahead and start with our first speaker today. It is Eugene Sobecki. He is the Director of National Sales and Military Business Development. He is going to be talking about the Pine Creek Emergency Bridge in Somerset County, Pennsylvania, about their modular steel bridges in action. So, Eugene, the floor is yours.
Hey, thanks. Yeah, I'll be discussing this project in a little bit of detail, something that we just did very recently. And then I'll also be, highlighting another project we did in the past, which is the same one where it highlights steel in action. So to get started on this project right now, what I'm going to talk about a little bit is the challenge and why our stakeholders choose steel and why emergency steel bridges are an answer for a lot of situations. About the Piney Creek project, and then about another project we did on the West Coast, and then at the end a little bit about ACRO and question and answers, which we can defer to the end of the presentation. Most of the challenges of all these bridges out there that need to be replaced have been highlighted in the ARPTA report. I don't know how many people access that, but it's a good database to find out exactly what's happening in our market. In the last one in 2024, it said 36% of all U.S. bridges require major repair work and replacement, and over 200,000 need repair, including another 76,000 bridges that should be replaced. So sometimes they need to get replaced a little bit before they're scheduled to be replaced due to washouts and storms and incidents, which I'll talk about here in the next couple projects. Again, to the challenge that we all face is the aging infrastructure that ends up with bridge closures and traffic destruction, structural deficiencies in old structures, high maintenance costs, rapid response that's required, and a lot of times remote access and getting to these sites that could get damaged in these natural emergencies that come up. Why emergency steel bridges? A lot of the times I choose steel because of the cost. The speed of assembly and installation is a lot quicker. Safety, versatility, transportability. It's easy to get our bridges into a lot of different remote locations. Sustainability, durability, and also the reusability of our structures. The challenges at Piney Creek in Boynton, PA, goes back to heavy rains that came and causes the flooding of the Piney Creek Bridge. And you can see from this photo too, it's at the confluence of two rivers that's coming into the Piney Creek. And that's the replacement bridge on the bottom. Unfortunately, I didn't have pictures of the old bridge, but this is the replacement bridge that was put in place. And this happened back in May 14th, this year. PennDOT closed the bridge. They put detours in place because they had to get the traffic around it because it was handling about 4,700 vehicles a day. Again, too, this is the project view. This is our bridge in place already. And you can see, it's kind of hard to see in this photo, but there are power lines just north of the bridge, which cause a little bit of concerns when we're doing the installation on placing cranes to get it into place. The project requirements required, speed of assembly and installation to get it open as quick as possible. The assembly and launching on alignment because they didn't have time to come up with an off alignment situation right now. So we are on alignment of the original bridge. And then we also had to give them full on-site technical assistance. And because this project went 24 hours a day until it was completed. And then we had to have full technical compliance based on PennDOT requirements. This is basically the structure that we proposed to them. It's our panel bridge, which makes it a little bit easier. It's all just based on modular units that we call commercially off the shelf. We keep these in inventory all the time so we can really respond to these emergencies. One of the main is the panel. The other is a transom, which dictates the width of the bridge. And then our decks, which are all 6x10 units, whether they're curb or if they're an infill deck. So we can use these pieces and parts. They all sit in our warehouse locations in New Jersey, Pennsylvania, Memphis, Tennessee, and also on the West Coast in Centralia, Washington. The specifications for this project required a 100-foot long bridge that had to be 30-foot curb to curb for two 12-foot lanes and 2-foot shoulders on either side. They wanted it paved with a crowned asphalt overlay to account for drainage off the bridge. It needed a guardrail system designed to meet the TL4 loading criteria, and it had to meet full PennDOT design, which was PHL 93 for legal, their P82 permit loading, all as per their PennDOT design manual part 4. Talking a little bit about the project timeline. Like I said, they closed it on the 14th. We got our call very early the morning of the 15th. If you went to our website, there's some emergency contact numbers. Unfortunately, I'm one of them, so it means I always have to answer my phone, whether it be 2 o'clock in the morning or 8 o'clock at night. So we received a call on the 15th telling us about the problem, first from the design engineer and then from the contractor. By that same afternoon that we received the call, we already determined the span length and width that we had to use. And that evening, within about 10 hours, we sent preliminary reactions to the contractor, which was Merlo, so they could start designing the bridge foundations. And by Sunday, the 18th, we had full drawings and calculations completed. The full submittal package was then sent out on Sunday night, so they had it first thing Monday morning. The bridge was loaded out of our New Jersey facility on Monday, the 21st, with the components arriving the next day on Tuesday at the site. So here we take project timeline day 6, which is Tuesday. So already we have our field service representatives on site, giving them full support during the build of the Acro Bridge to give for guidance and safe and efficient assembly of the bridge. And we had our one FSR on site who was out there for most of it. We had to relieve him because this was a 24-hour project to get this bridge reopened as quickly as possible. Again, which meant working at night. This is some of the overnight assembly of our bridge system as they were putting it in. The bridge was actually constructed on rollers. If you can see it, look on the base of the bridge, you see some green, looks like on top of the blocking. That's our roller systems, because the bridge had to be installed by a crane-assisted launch. Because again, too, if you just look north of this photo, you can see the power lines that are right next to the bridge. So very difficult in getting a heavy piece of a crane to lift it and pick it. So they decided to push it across and use what we call a crane-assisted launch. By day 7 comes around, which is Wednesday, the crane arrives at the site, and so they can, again, too, use the what we call crane-assisted launch, where they support the doze as it comes across the bridge, and then it'll eventually be able to get the bridge and put it down on the bearing. So that was all accomplished by Wednesday, the 21st. So and at 6:30 at night, again, to working 24 hours a day. And then they went right into preparing the bridge. This is the approaches that they had to add the asphalt into the approaches to bring it up a little bit to the correct back wall height. Not too much of an elevation change, but just enough that they needed to put a little bit of asphalt in to bring up the approach roads to meet the new alignment of the bridge. And then Saturday rolls around on day 10, and the bridge is open to traffic, getting it done in less than 2 weeks after the closure. So we were able to get this open to traffic and keep everybody happy within approximately about 10 days to get the whole project done. So that was a quick action, getting all the stakeholders involved and getting everybody with the DOT, the consulting engineer, and the contractors, and our on-site supervision, along with our operations department and engineering team, to get it done within 10 days. And the final result was a rapid connectivity. Again, too, like I said, working in partnership with all the major stakeholders. Again, the design and supply of the bridge was by Acro. The contractor was Merlo. Engineer for PennDOT was Gannett Fleming Trans Systems, and the owner, of course, was PennDOT. Accelerated bridge construction with Acro, again, too, because of the speed. Again, using the steel makes it quickly. This is all off-the-shelf material. So we reduced downtime, optimized the cost, allowed for a temporary bridge to be launched in less than 2 weeks. The solution allowed us to restart traffic quickly with a very easy installation. And the service and support, we had technical people on site within 24 hours of the closure to first do site assessment and then to ensure a smooth installation. And safety, because all our site supervisors are trained in safety operations, so we make sure we have a very safe installation and safe working practices for all at times, because that is extremely important. Other emergency projects, again, too, our bridges use a lot of emergency projects because of the accelerated steel bridge construction, rapidly assembled and installed. We can customize it easily, again, too, because it's almost like I hate to say this all the time, but a big erector set that can be, put together to get the spans, the widths that's required. We can support fully highway load carrying capabilities and heavy duty permit applications. And the steel facilities are fast and easy assembly and disassembly with minimal equipment, which again, too, drives the use of steel for these replacement projects. We can handle typical design criteria for these projects like Piney Creek or loading design. We can do whatever is required, ASD, LRFD, MLC for military or heavy haul. We have a variety of different bridge types. The one used on Piney Creek, we used plain steel with an asphalt overlay because we needed the crown in the center for drainage. We can also do a steel deck with an anti-skid coating applied to it, which actually gets the bridge open a lot quicker because you don't have to asphalt the deck once it's placed. You just drop the deck and you're good to go. We can do timber decks if it's a little bit more heavier loads and point loads on the wheels. And then we can do stone-filled pans if required in rural locations. And all our guardrail is designed for TL1 through TL4 requirements. Like I said, the bridge is designed to meet ASTO, ASD, HS20, 25, HL93. Our widths can go from 12 to 42 foot curb to curb. Our single spans can go from 10 foot to up to 300 foot for a single lane. We do about 240 to 260 for a two-lane bridge, clear span, that's unsupported total for that length. And then we also do pedestrian bridges. And then, of course, if the bridge has to be longer than the 240 or the 300, we can do multiple spans, whether they're independent or continuous. Our bridge deck is a steel orthotropic deck system, all 6x10. And like I said, the driving surfaces can be a variety of asphalt, anti-skid, plain steel, or wood. This is another example of another emergency project that we were involved in, I-5 bridge collapse in the state of Washington. North is Seattle. This bridge went down, so we provided 2 bridges within a week. Start to finish for this whole project was in 15 days. We put in 2 bridges, 160-foot clear spans. Both bridges were 24-foot curb to curb, full design loading to HL93 because it was a state interstate, and designed with TL4 guardrail system. I just have a couple of quick pictures of why this bridge happened. This is state of Washington design on a lot of their overhead trusses, what they put out. And actually, if you look at the center here, their actual height is about 18 foot and the published height is like 17.9. So when they put the permits out for overheight trucks, they're usually maxing them out at 17 to actually give them a good foot clearance. But if you look over to the right, the actual height is only 15.6. Now, this is what caused a problem on this bridge because the truck had the permit for overheight, but the permit was supposed to go down the center of the highway. Well, unfortunately, he went a little bit to the right and clipped that overhead truss. When he clipped the overhead truss, we had a total compression failure of the top cord, and that 160-foot span ended up in the drink of the river there. You can see it here. A couple cars went in. Fortunately, nobody was fatally injured on this project, and just a lot of minor injuries. But you could see a good thing of compression failure of that top truss just because they clipped that one truss on the upper right-hand corner. So we were called into this project pretty quickly. It happened on a Thursday. By Friday, we had preliminary designs put together. And we said, oh, okay, we can't do a 4-lane bridge as the interstate required, 48 curb to curb, but we can do two-lane bridges. So we came up with a design for two-lane bridges, 24-foot curb to curb, side by side to open up this interstate. Again, critical interstate, basically the main route between there and Canada heading north out of Seattle. So the pressure was on to get it done. And part of the pressure was generated by Costco, who was at one end of the bridge, and they were losing $1 million in revenue a day because the traffic could not get to the Costco store. So it tells you a little bit of the strengths of the local community. So we started delivering steel like I said, this happened on the Thursday, and of course it happened on the Thursday before Memorial Day weekend, because emergencies never happen on Mondays at 9 o'clock. They always happen on Friday nights or before a long weekend. So we were able to get steel across the country and into this location by Tuesday morning, and then we started building bridges on the approaches. And here too, you can see some of the steel that's being lifted into place. We had to do a double height truss configuration, and we had to build one bridge at a time. And then we had to launch it across this gap to go into the other structure. For this bridge, we had to use a launching nose because we had to go through the other end and almost like thread the needle of getting this launching nose into the other trusses on the other side. So here you can see the launching nose. Well, that single height truss configuration that you see going from right to left is our launching nose. That's only there to help launch it across because we couldn't get any cranes to lift it and pick it into sight on that river. This shows like the first span going into place. That's all the way through. You could see how tight it is as we had to shoot through the existing bridge that was still in place. We had to get our structure right up into those trusses. So that was the first 160-foot span we put in place. And then we went to the second span to drive across and move it into position. Part of the problem was that we didn't have a lot of room to get that done. So as we pushed one across, we had to put it down, and it's hard to see on this, but on the very bottom of the photo, you see like a beam going across where that one worker is standing. That is actually a beam that had movable bearings on it, so we could slide the bridge back and forth. Because as you can see, as the second bridge is coming into the first bridge, there's no way that's going to fit. So they had to take that first bridge and then move it over to the right so the second bridge could finally fit in. And this is it as it's coming across the second bridge. You can see now we got clearance. The old bridge is on the right-hand side without any issue, and the second bridge is making its way across. This is another photo showing that the launch of the second bridge as we're coming across into meet up with the existing bridge. And then finally, we got both bridges into place. They fit in. We moved them over, slided everything into place, got them down on the final bearings and ready to go. What's nice about the system too is that the deck is all secured from the top. So once the bridge is in place, they lay the deck and they can come down and just attach all the decking from the top. There's no reason to go underneath the bridge to attach the steel deck. And then after that, we had an application of our tack coat. Because again, too, this was a mainline interstate, so they wanted to have it asphalted. So we came up with a system of going a tack coat and then using a fabric, and then going with a final asphalt application on top of it. And then we did our final inspections. Here we're just waiting to do the final striping on the bridge, but it's all ready to go. And then the bridge is finally in place and it's open to traffic within 14 days. And we could have done it earlier than 14 days, but the NTSB had it shut down for 4 days because it was considered an emergency site because there was cars that were in the drink and they had to do their full investigation first. Again, why steel? Availability, the cost, sustainability, significantly less time in site due to prefabrication, no forms to build up or strip, better quality control, no negative impacts by weather, lightning, etc. We have precise fabrications. Everything is done robotically in our plant in Milton, Pennsylvania. With the new steels, we can get a lighter and weight and strength ratio. Our steel is 100% recyclable, easier to modify, historically proven in steel bridges, easier for maintenance and inspection, again, too, because it's all galvanized, and achieves longer spans, less expensive, and then quicker installations. And then why we are around, because we have this proven technology that we've been working on since the 60s. We manufacture in the U.S. using all U.S. high-quality steel. We can customize it to what's required. We have our precision engineered design for safety and durability. Again, like I said, it's hot dip galvanized, eliminates corrosion, minimizes all maintenance. We got very rapid installations, as you can see from these two case histories. And we have engineering support from start to finish on any project, and we're in, with all key stakeholders. Like I said, Acro's been around since '51. We're based out of Parsippany, New Jersey, manufacturing locations in Milton, PA, and we're also in the UK. And then we're also now are the owners of Maybe Bridge and Shore, which used to be our other panel bridge system. And we have staging yards throughout the United States. Again, just recapping key applications from vehicular to railroad to detours. We even do movable structures. So we have a lot of different options. So in a nutshell, I think I did it under 23 minutes. So any questions?
Right, yes. It looks like a couple of questions. Is this the Bailey Bridge that of the Corps of Engineers have had for years?
It's based off the Bailey Bridge. This presentation, and normally I start off these presentations giving props to the Bailey Bridge. Bailey Bridge was designed for World War II in 1936. So this is all based on Bailey Bridge technology. Same thing, but it's same thing but different. So it's like I always say, it's like using a copier. You have one copier that does so many functions, and then you have other copy that can do a lot more. So this is like newer technology, higher strength steels. We do wider width, but it is based on the old Bailey Bridge system.
All right, perfect. Let's see, a couple more questions. Why Western Coast states, Texas, Florida, rarely use steel bridges? I feel like that might be a false.
I would say it's. I mean, for us, it's. I mean, we right now we've been doing a lot more temporary bypass work in Texas than permanent bridges. But on the West Coast, California, state of Washington, and the great state of Hawaii are some of our best customers for steel bridges. And if anybody ever wants to go to Hawaii, I'll give them a scan tour guide and they can take a look at the bridges for me.
Which is the weight of the steel structure per square foot?
It all depends on what I'm looking at, because as you saw in some of the pictures, the trusses on the side, we can change the truss configuration based on the width and the span and the load. So it can vary all over the place. And so it's very, very hard to come up with a pounds per square foot because I'm changing that weight for the applications I need. Because seeing that we are a through truss, we're getting all our support on the trusses on either side of the bridge. So I can do two trusses on one side. I can do, four trusses on each side, and I could do four stacked upon four. So, it really depends on the actual bridge length. So there is no real easy answer for pounds per square foot of bridge.
And a couple of questions that go kind of hand in hand. What is the typical design life associated with acro bridges? And then, do you guys use galvanized steel?
Well, of course, we use galvanized steel, or else I wouldn't be here. No,
Right answer, right answer. Just
no,
kidding.
we've been using galvanized steel since I want to say the original structures used to be painted, and even the old Bailey structures were painted steel. So we switched to all galvanized probably in the mid '90s, like say '95, just for its durability and reusability. So, and we design them as permanent bridges. I always say our bridges are designed as permanent bridges, but they can be used as temporary applications. So if you need a design life of 75 or 100 years, yes, we can give you that design life in our structures.
And about 300-foot simple spans can be achieved.
We've done 300-foot simple spans. It's probably with the newer loads and stuff, we're probably back down to maybe about 270 on a single span bridge. Uh, we've done a lot of two-lane 24 bridges. We've done a lot in the 240 to 260 clear spans. What happens is the bridge starts getting so heavy that it's not a design problem, it's an installation problem of the bridge. Because number one, it started to get too heavy for a pick, and it starts to get too heavy to launch it on rollers. So we like to say a two-lane structure, we like to say in that 240 to 250 for a two-lane 24. But like I say, just for an instance, and a project we have on the 101 in Northern California right now, it's a 1,000-foot bridge. It's all based on two-lane 24, 200-foot independent spans as it goes across the Smith River.
Here's an interesting question. Have you used the system for pipe bridges?
Yes, we use pipe bridges, utility bridges, uh, pipe supports, truss supports, you name it. I mean, that's a whole nother presentation on the versatility of our bridges. I mean, we've done all types of pipe bridges.
Okay. We'll do a couple more before we hand it over to Joel here. We have a lot of design life. So even though temporary bridges, what is it expected life of a temporary bridge?
Like I said, 100 years. It's not. It's funny. I always say, people say temporary bridge, and they assume there's an end life of it. But like I said too, it's designed like a permanent bridge. So it's designed to have your 75 to 100-year life cycle. Uh, Another just an interesting story. We did a project in Chicago. Manufacturing the bridge is still there. When they, I think it was back in 2013, and when they put it in, they knew it was going to be a temporary bridge, but they didn't want to tell the people in Chicago that it was a temporary bridge just for that reason, because people hear temporary and they think it's going to have an end life very quickly. So the city of Chicago, they coined their own term. They call it an interim bridge, which they sort of
Yeah.
felt it doesn't designate an end life, which it doesn't. So temporary can be a misnomer. That's why we say there are permanent bridges that could be used as temporary applications.
All right, well, we're about halfway. So we'll go ahead and kick it over to Joel. Joel, if you want to go ahead and share your screen, we can get that up. Now, Eugene is going to stick around. He'll be online. Eugene, maybe take a look at those Q&A questions, see if you can't answer
Yep.
any of those. If for some reason we get a ton of questions, which we already are, we will go ahead and answer those offline later if we don't get to them all today. We have everybody's email address. So thanks once again. And next up is going to be Joel Ham. He's senior engineer with Contact Engineering Solutions, and he is going to be talking about um, corrugated steel. Go ahead, Joel. Yeah, it looks like everything's ready for you. Floor is yours.
All right. Thanks, Jeff. And thanks everyone for tuning in. Um, I'm a senior engineer at Contact Engineered Solutions. My primary role there is to work with with people internally in our organization, mostly on the sales side, and also with agencies, consultants, contractors, and others to help develop, design, fabricate, and support buried bridge projects. So I've worked on hundreds of buried bridges around the country and some internationally. Seen a lot of different types of things being done, and happy to be here to share some information on case studies with you. So if just in case some people aren't familiar with what buried bridges are, I'll just go through a very brief introduction. Buried bridges are bridge length structure that generally 20-foot span or greater that supports loads through soil structure interaction using the backfill around the structure. So the buried bridge consists of the structure shell itself and the backfill around it. These structures are made of corrugated metal and are flexible, which provides some design and performance advantages. The buried bridges have been the topic of numerous webinars, workshops, and conference sessions dealing with various aspects of design, construction, and other items. Some of those you maybe have heard through the Short Span Steel Bridge Alliance or with ASHTO or TRB. These structures conform to design codes and standards worldwide and meet requirements for materials, design, construction, and load rating, and are not proprietary. And these structures are designed using finite element analysis, which is a little bit different than what you may be familiar with if you have experience with some of those smaller drainage structures, or some people call these culvert bridges. I don't think that's very accurate, aside from the fact that they're both corrugated, but that's one of the main differences there. There are two main categories of metal buried bridges, which is based on the corrugation profile depth. The corrugation profile is measured from peak to valley. So peak to peak for the width and then peak to valley for the depth. Anything has a corrugation depth of more than 5 inches, 5 inches deep or deeper is considered deep corrugated. Anything smaller than that is shallow corrugated. On the picture that I'm showing here, those are the three most common steel corrugation profiles. You have one deep shallow corrugation profile, the 6x2, and then you have the 15 by 5.5 and the 19 by 9.5. One of the biggest advantages of deep corrugated steel is that when you're comparing the 15 by 5.5 to 6x2 profile, deep corrugated steel is about 9 times stiffer, and it's over a third stronger, sometimes double the strength. So that means we can get into much heavier loads and longer spans, which gets us into the realm where these are a viable alternative to conventional bridges on a lot of projects. In addition to that, these structures are flexible, and there are some definite design and performance advantages that you can take advantage of that if you're willing to consider that as part of the design and the development of those projects. There are a number of advantages and applications. I've listed a few of those here. The most common ones, generally you can use this anywhere where you can use a short to medium span bridge. If you're spanning water, spanning a road, spanning a pedestrian path, and then as far as carrying the loads, they can carry anything that a conventional bridge could carry, including some very heavy loads like rail and mining type loads. Structurally, these are redundant and resilient. There's some big advantages there. By definition, almost all buried bridge projects are accelerated construction projects. So there are a lot of construction and constructability benefits, foundation costs, and from maintenance and inspection that's much simpler than a conventional bridge. So moving into our case studies, I have a handful I'm going to share with you that are talking about some different aspects, kind of a range of capabilities, just to help visualize where and how they're used. The first one I'm going to talk about is at Audubon Hollow. This is in the Galleria area in Houston, Texas. This was an area that was previously undeveloped, but surrounded by developed areas with only one way to get in and out. So they, in order to get in and out of the site, they had to span a pretty large drainage ditch area. And they decided to go with a 32-foot span, deep corrugated arch structure. And because of work that needed to happen before the project could be fully designed, there was a need to get in there before everything was fully figured out. So they decided to go with stage construction with the buried bridge structure, where they would put the structure in there, put in a single lane access road so the contractor could do some of the upfront work while they were working through the final site design to finish the project. And another neat aspect of this is that there's an architect involved. This was kind of a high-end residential development, and they selected this type of a structure and also wanted to use recycled concrete backfill for sustainability reasons. And that we were able to incorporate that on this project, and they also wanted to use MSE welded wire head walls, mainly for the aesthetic look of them. It's not very often that Google Earth times their pictures in ways that benefit projects, but on this one, there happened to be two pictures taken during construction. The first one here shows the first phase where the structure's been assembled, and then the contractor's access road is in there. They're doing some work. The rest of this hasn't been covered up yet because the civil engineer hasn't decided what's happening at the end of the structure with finalizing the site grading. This picture is after the second phase is done, that the structure's in. I don't think they've quite finished with what they're doing with the end treatments here, but it's far enough along where the bridge itself is actually done, and they're moving forward with construction of the houses in the area. The picture on the left is during that first phase where the road is in. They put a temporary MSE wall in there, and until they figure out what's happening at the end of the structure here. The structure on the right is actually on the other end of the structure shown here. They were right up against the property line on that side, so they didn't really have much of a choice of what to do with the end treatments there. And with the MSE walls, they're able to build them vertically and put them pretty much right at the property line. This is the other end of the structure after it was completed. So they finalized the layout. They're able to kind of curve, and that's a neat feature with the wire head walls, is you can pretty much make them look like and go wherever you want them to. And then finally, after it was finished, they added their architectural treatments, some barriers and some ornamental railing, and the project is finished. This next one is in Attleboro, Massachusetts. Temporary bridge built as they were going to replace two 3-lane I-95 highway bridges. This is south of Boston. And as they were replacing each of those bridges, they wanted to build a temporary bridge in the median to carry the traffic, to not have to do any detours or disrupt things so much as they're doing that work. Originally in the project documents, they were specifying a Bailey Bridge in that area. One of the contractors bidding the project reached out to us to see if there might be a buried bridge alternative for this. And we were able to come up with that. The structure had to be sized to accommodate basically 2-lane highway clearance plus pedestrian walkway on either side of the road through the structure without changing the final grade above. And we were able to do that and ended up saving about 4 months on the project and over $1 million, and essentially helped that contractor win the project. This structure consisted of 3 plates for each ring. Each ring of the structure is 2 full corrugations, and the plates are 2.5 feet wide. So 5 of those plates bolted together form that structure shape. 100 plates total, and the contractor who had never built one of these structures before was able to assemble the entire structure essentially in one day. They were given a weekend to close the road to build it. And they took the first day to do the assembly, and then the second day was final tightening of bolts and then getting ready to place the backfill around the structure. We also use MSE wire walls on this structure to limit the footprint of it to avoid conflicts with the abutments for the new bridges when they were being placed. The contractor, in order to optimize the time that he had to do the assembly, pre-assembled the 3 crown plates of the structure off to the side so that he could bring those in as a unit to install more quickly on the foundation. So each ring of the structure involved setting the two side plates, and then they would bring in the 3 crown plates as if they were one large plate and bolt them in. This backhoe here is the biggest piece of equipment that they use for the assembly of the structure. And this is typical on most projects, unless you don't have access nearby where you can, where you don't have a long reach. So this was built during the spring of the year, so they finished in the dark, and this is them getting close to the end of the structure. This gives you an idea. Since this was a temporary structure, they weren't really focusing on what the head walls were going to look like. Normally, you'd have like rock facing, similar to the Audubon hollow structure. This type of system. In this case, they just used the geotextile to speed things along. But this gives you an idea. There's room here for 2 semi-trucks to pass each other, plus plenty of room for pedestrians to cross on either side. Another view as we're nearing filling over the crown of the structure. You can see the grid strips for the MSE walls here. This is at final grading shortly before paving. This structure was actually instrumented and incorporated into an NCHRP research project that was looking at load rating buried structures. The results of that are available in a report. If anyone is interested in seeing it, I can provide that, or I can get that to you. Ultimately, what it showed was that the way that we're designing these structures is probably a little bit conservative, using the AASHTO requirements, and it also validated the finite element design models that we're doing. So it gives a lot more confidence for the design of these larger structures. This was in service for about 1.5 years. Once the bridges were completed, it was taken out and has probably been recycled already into who knows what, because steel is the most recycled material on earth. This next project is pretty unusual. This is one of those things that I'll maybe never get to see again. This is also a bridge replacement up in Alaska on the Klondike Highway. This is close to the border between Alaska and Yukon Territory. This had I think it was about a 250-foot span suspension bridge that wasn't able to handle the traffic anymore. The anchorages were starting to pull out of the foundation, but they still needed to have a bridge there. This is a pretty harsh conditions. There was a deep ravine about 100 feet deep with a pretty steep stream flowing through it. Pretty harsh conditions. So they working with the engineer to develop a solution here. We ended up coming up with a 75-foot span buried bridge that would be backfilled with roller compacted concrete to provide the new bridge through there. Because of site constraints and just the site limitations, the structure had to be skewed quite a bit, about 18 degrees on both ends. And then to make things even more interesting, there really wasn't a way to get inside the structure during construction to do any of the stuff that needed to happen with assembly. So we ended up designing this structure for the special site conditions and requirements, and also detailing it so that the whole thing could be built or set on the foundation, built from the outside. This was our geometry. It was a 75-foot span by 25-foot rise, multi-radius arch. At the time it was built, this was the longest span flexible buried bridge in the US. There were some additional features added here for the modular construction. One thing was 4-inch by 4-inch rolled angle placed on the ends of each segment. So the structures could be set on the foundation and then they were butted up to each other and the rolled angles were bolted together. And that's essentially to close the gap. There was because this structure had a skew on it, we came up with a system using beams that would be bolted onto the complete rings of the structure and essentially cantilevered over the skewed ends of it to provide temporary support of the skewed portions of the structure as the concrete was being placed around it. This is a plan view of what the structure looked like for the phasing with the main barrel and the skewed ends. This middle section here is 20 feet wide, and then the skews were assembled separately, and then so we would first set the middle section on the structure, and then the two outside sections, and then the beams would rest in these rectangular areas here. There would be I believe they were bolted onto there, and then the fill was placed. At the end of construction, these plates were intentionally left long to accommodate formwork for the roller compacted concrete as it was placed, and then those are trimmed after the construction was complete. This gives you a little bit of an idea of kind of the extreme conditions here. They had to do some trimming of some loose rock on the above the project for safety reasons, and I think to accommodate some things that they wanted to do when they placed the RCC. So I don't know who's more nervous in this picture, the guy in the crane or the guy in the backhoe who's doing the excavation. But sometimes that's just how you have to do. You got to figure out a way to get things done in areas like that. This is a staging area above where the structure was being set, where they pre-assembled everything, and then they would pick it up with a crane and lower it onto the foundation. So in the foreground here at the bottom left, you can see that that's one of the skewed sections. The other skewed sections on the other side of it, and the middle section's already been placed into the hole. So here's that first phase placed on the footing, and then they're flying in one of the skewed sides below, set it down, butt them up to each other, bolt the angles together, and then do the next one. So here the whole structure has been assembled. The beams have been installed. On the left is the foundations before, and then on the right is after the structure's been assembled. They've already started with placement of the concrete fill. The structure was designed to accommodate essentially 5 feet of cover using concrete as a fill material. The project engineer determined that once they had 5 feet of concrete over the structure, that the concrete would be able to provide adequate support for the placement of the rest of the roller compacted concrete. So in this case, for this application, the structure essentially acts as a stay-in-place form for the complete structure. So here's another view with the assembled structure partially backfilled with the existing bridge behind it. They placed a site batch concrete around the structure until they got 5 feet over the top, and then from there on up was roller compacted concrete, which was essentially slip formed. I think this ended up taking place over 2 construction seasons. And there, it's kind of hard to get a good view of it at the end, but you can see that the completed roadway here with the structure underneath it. The existing bridge was left in place and is now used for recreation. So if you vacation in the Skagway, Alaska area, you could go see both of those bridges. This next one, I just kind of threw in at the last minute. I received some information this week about the performance of this structure. This was one that we had built about 5 years ago in Burnett County, Texas. This is in the area where we had that extreme flooding last week. This was the Knife River yard. Knife River is a quarry there, and this is the only access in and out of the quarry where they're crossing Honey Creek. During the flooding, the structure that we placed in there was a 50.5 foot span by 11-foot-8 rise, low profile arch. So a pretty low profile for an arch shape. Also with MSE wire head walls on it, designed for Cat 770 haul trucks. So it was essentially a haul road for the quarry. My understanding was that this structure and the walls were overtopped by about 10 feet during the flooding. The floodwaters removed the concrete barriers above the structure, stripped away some of the pavement, and the fill down to the first layer of the geogrid for the MSE walls. The image on the right was one of the earlier iterations from the design. I just put that in there to give you an idea of sort of what the site looks like. They have there was shallow bedrock here, so the structure is essentially bearing on rock. So fortunately, scour was not going to be a concern with the performance. This is the geometry that we placed. So a pretty low profile arch without a lot of cover on it. So about 15 feet from bottom of structure to essentially the top of the walls there, with a little over 3 feet of cover. We received these pictures from the mine or from the quarry as they were informing us that the flooding happened there, and they're just looking for an assessment of the structure and the walls and seeing what to do next. We haven't been out there to assess conditions for ourselves yet, but based on what's been provided so far, it looks like the structure has performed very well, and the walls is also so far it seems that it's just going to be some repairs near the surface to get them going again. So in this picture here, this is downstream of the structure. I believe these are the concrete barriers that are shown in the foreground. I don't know if those have been pulled from the stream or if that's just where the water left them. So you can see what happened with those. The road, a lot of the road here is missing. Some of the fill is missing off the top, but the presence of the grid strip reinforcing here, I think helped to minimize the amount of the fill that got washed away. Another view, closer up view, the structure looks to be pretty much like new here. We'll get a better idea once we get down there and get a closer look at it. The wall alignment stayed good. One of the benefits with using this type of a wall system is that it's essentially self-draining, and it is pretty durable even for impacts and things like that. Another view here is the downstream end on the left, and on the right is the upstream end. Some debris build up, but again, the wall is in good shape. No visible damage to the structure. Looks like it's doing pretty well. So I'm just going to wrap things up here with a couple more snapshots of a handful of projects and then get to some questions. This project is out in Spokane, Washington. Similar application to the Audubon Hollow, even a similar size structure, but in this case we had 40 feet of cover and there was a busy US highway going over the top. So in this case, they excavated half of the road, put a soldier pile and lagging wall in, and built half the structure, then backfilled with a temporary MSE wall, took out and then excavated the other half and continued building the structure. This was a creek crossing with rail loading. Again, there was a pretty tight site constraints on this project. There was actually big major flooding in the area during construction, but the structure held up and is carrying train loading. bridge replacement project in Pennsylvania. This is similar, basically the same type of an application as the one I just showed with the train loading. In this case, it's just essentially a township road with much lighter loading, but similar size structure, similar application. So a lot of times we can use the same solutions in a lot of different scenarios and site and design conditions. There's a steel bridge replacement in Maine, 20-foot span bridge replaced by a slightly larger buried bridge, where we incorporated the existing bridge abutments into the foundation for the new structure. Another similar type of structure built in Craig, Alaska. This one was selected specifically because it could be built by the local tribal forces. Multi-radius arch structure in Tennessee. This one is kind of illustrates what's possible if you have the room to let structures go a little bit long. A lot of times you can save cost and maintenance issues by just using a step beveled ends. Even if the structure is skewed with the roadway, you can use different length bevels on different corners to accommodate whatever those slopes of the fill are. Bridge replacement project in Ohio. This was under I-75. They were adding a lane in each direction, going from 4 lanes to 6 lanes. So rather than building more bridges, they built a buried bridge and then just moved traffic over in a staged way as they were rebuilding the roadway and paving over the top to create the new wider interstate. This is a rehabilitation of an existing concrete arch in Kansas, also underneath I-70. With this material, it's pretty easy to, if we have good measurements of the existing shape, we can get pretty close with matching with the new structure, providing enough space in between the two to place grout to kind of close that gap and help them operate together. Another great separation project in Nebraska. This is a loop track at an agricultural facility, sized on the inside to accommodate 2 semi-trucks passing each other and designed to carry rail loading over the top. Project in California, there are 4 crossings like this over pedestrian walkways. These are fully beveled for aesthetic reasons. This is at the site of the old El Toro Marine Base, where they had the blimps during World War II, and also operate in other ways since then. After the base was closed, they wanted to redevelop it into a green space and incorporate several of these structures. They also use the existing runway concrete as backfill around these. So another sustainability project. Another California project that was basically took what used to be a low water crossing that flooded frequently and make it into a signature entrance to a city park. So from a technical or design standpoint, fairly straightforward, but aesthetically, you can make these structures look like just about anything you want. Great separation project in Lacine, Kansas. This was sized to accommodate a double rail crossing through the structure and a county highway over the top, with kind of a challenging at a challenging angle where it essentially turns a corner and crosses over. So with the MSE walls, we're able to accommodate what the grades needed to be there. And then wildlife crossing in Banff, Alberta, Canada. These are becoming more common. They're popping up, especially out west in the US. And these types of buried bridges are a very good solution for these types of applications.